Light, reflection and refraction. Lecture number 2. In this particular lecture, we will be dealing with the concepts of magnification and refraction of light. So let's start with magnification. So coming to the magnification part of the lecture, let's start with the introduction. Okay? So let's talk about when a magnification is produced. A magnification produced by a spherical mirror gives the relative extent of which the image and object are magnified. It is expressed as a ratio of the height of the image to the height of the object, and it is represented by the letter small m. So for a better idea, if at all you take h to be the height of the object and h prime to be the height of the image, then the magnification m will be given by m equal to the ratio of the height of the image and the height of the object. So let's solve an example on this concept. Given below is a question. So from the question I have these values and I have to find out d and h. So by using this formula and on substituting the values and on simplification and on further simplification, I get 1 by d equals 0.0439. So my value of d will be 22.8 centimeters. Now my job is to find out the height of the image. So by using the following formula and this, I detect the value of hi, which is 1.99 centimeters. So let's start with the refraction part of the lecture. Usually, when a ray of light falls on the boundary of separation between the two media, there is a change in the direction of the ray. This is called as refraction. So to get a better knowledge of what refraction is, we shall be learning about the laws of refraction. So let's proceed with the law of refraction. Like the law of reflection, here are also two laws, two simple laws. So coming to law number 1, this states that the incident ray, the normal at the point of incidence and the refracted ray all lie in the same plane. Now let's go to law number 2. This states that for the same pair of media and the same color of light, the ratio of the sine of angle of incidence to the sine of angle of refraction is always a constant. We will be learning further about this in the further part of the lecture. So now I'll be giving to you a real-time example of refraction. Have a look of the diagram below. In this diagram, you see that the image of the fish will be seen a bit above than its actual position. The reason for this is refraction. Now let's learn why this happens. So let's start learning about the refractive index. As told ago, it is the ratio of the sine of the incident angle and the ratio of the sine of the refracted angle. Given below are the images and this is the formula where theta 1 is a I and theta 2 is R. So let's start about the principle of reversibility of light. As light follows a reversible path, we have sine R by sin I is n12 and sin I by sin R is n21. Therefore, 1 by n12 is n21. You have to mark this up. Now let's learn about the critical angle. We know that the refractive index can also be expressed in terms of the ratio of velocities. Hence, for any particular medium, the value of n will equal to the velocity of light in air to the velocity of light in medium, which is equal to 1 by sine of c. This new quantity c is called as a critical angle. Okay? Now let's study about an interesting phenomena, which is the apparent depth in a liquid. As the name suggests, it says that if an object, when placed at the bottom of a transparent medium, say water, when viewed from above will appear higher than what it actually is. The refractive index in this case is given by the relation n equal to real depth by apparent depth. So after this, let's study about the refraction through a single surface. So for this diagram, if u1 and u2 are the refractive indices of the first and second media and r is the radius of curvature, then the formula is given by u2 minus u2 by v minus u2 by u equal to u2 minus u1 by r. This is the formula. Here I consider u2 to be greater than mu1. Here u and v are the distances of the object in the image from the center of the refracting surface, and r is the radius of curvature. Please note that. So let us consider another case. Here I have the radius of curvature to be taken to be positive, and u and v are the image and object distance. In this case, I get m1 by u plus m2 by v equal to 0. Now let's solve an example on this. Given below is a bit lengthy question. Please read it. So if I solve for the flat surface, these are what I have. So by using the formula, I get m to be 1.6. And for the curved surface, have a look at the diagram. These are all the given parameters. So on solving for v, we get v equals to 33.3 centimeters. Please pause the video accordingly if you feel it's a bit fast or slow. So let's start with lens. Lenses are a bit different from mirrors. These are actually doubly curved spherical media. Since they are doubly curved, they have two radii of curvature. Let this radii of curvature be R1 and R2. Given below is an example or an illustration diagram of a lens. Have a look. Fine. In general, lenses are of two types. Concave lens and a convex lens. Please note the shape of the lens. It's very, very important. Now coming to the parameters of a lens. Lenses have more than one radius of curvature, and so they do not have a specific center of curvature. They rather have two foci, namely the principal foci or the principal focus and the secondary focus. These are present on the either side of the lens together. Now let's study something interesting, which is the method of image formation by a lens. So let's directly start with the rule number 1, which says that a ray of light coming from the object parallel to the principal axis after refraction from a convex mirror goes through the PF, and for a concave mirror it diverges from the PA on the other side, but it appears to converge at F1 on the same side itself. Have a look at the diagram, please. Done? So, coming to rule number 2, when a ray of light passing through a principal axis after refraction from a convex mirror will emerge parallel to the principal axis, and similarly for a concave mirror, it will also emerge parallel to the principal axis. It is the same for both. Let's have a look at the diagram, which will be shown shortly. So this is what it actually happens. The refracted ray will be parallel to the PA. Coming to the rule number 3, the ray of light passing through the optical center or the pole of a lens will always emerge without any deviation. This rule is applicable for both concave and convex lens. Have a look at the diagram, you'll understand it better. For both the lens, the ray through the optical center goes undeviated. Okay? Now let us study about the refraction through a lens and the lens maker formula. So if I have R1 and R2 to be the radii of the curvature of the first and second refracting surfaces of a thin lens of focal length f, then the lens maker's formula is given by 1 by f equal to n1 by n0 minus 1 into 1 by r1 minus 1 by r2. This is a formula. Please remember it. It's very important. Similarly, now let's move to a special case of the lens maker's formula. So here we have a lens surrounded by air. In that case, we have n1 to be 1 and n2 to be n. Then the formula gets reduced to n minus 1 into 1 by r1 plus 1 by r2. So this finally gets reduced to 1 by f equal to 1 by v minus 1 by u. The derivation of this part isn't that important. It's not at all important. But if at all you are interested, you have to go through your book. So let's study about the magnification by a lens. For a lens, the magnification is given by the ratio of the image size and the object size, given by the formula m equal to v divided by u. Now let's study about the power of a lens. The power of a lens, which is given by capital P, is the ability to deviate the ray towards the axis. It is given by P equal to 1 by f. Note that f should always be in meters. I repeat, F should always be in meters. And the unit of power is diopter. I repeat, diopter. Now, let's move on to the focal length of a series of lenses. So, here I mean to say that when I have a set of lenses, for example, I take two lenses which are placed together, then the effective focal length will be given by the given formula. Please remember this formula also. Now, coming to an interesting part, a new piece known as prism. A prism is a simple three-dimensional triangular piece made up of glass. It has some interesting properties. This is how it looks. To describe it, it has five plane surfaces, three on its sides, and the other two are its front and the back surface. Now let's move on to an interesting topic, which is the refraction of light through a prism. Interestingly, when a ray of white light is incident on the prism, the ray on undergoing refraction displays a spectrum of seven colors of Vimbue. This observation has led to several concepts which we will be discussing it shortly. Now coming to the various angles of a prism, please have a keen look of the diagram given below. In this diagram, you have A to be the prism angle, I to be the incident angle, R or R dash to be the refractive angle, D or delta which is the angle of deviation, and N which is not an angle is the refractive index of the prism. Note N is not an angle. Now let's study about the refraction through a prism in detail. So when we say a ray of monochromatic light is refracted by a prism, the deviation is produced is given by the formula delta equal to I plus E minus A, where I is the angle of incidence, E is the angle of emergence, and A is the angle of the prism. So the angle of deviation dm is minimum when a ray of light passes symmetrically through the prism. Then the refractive index n is given by the given formula, which is sine of a plus d by 2 divided by sine of a by 2. Please remember all these formulae. This will be very helpful. Now let's study about other type of phenomena. These are expected to be these are expected to be read by the reader. These are not much important, but if at all you are interested, you can have a look at these. So let's move on to the last and the important part of this lesson, which is the microscope. A simple microscope is given below. It is a short focal length convex lens. The magnifying power of a simple microscope is very high. Okay, note that it has a short focal length convex lens. Okay, a convex lens having a short focal length. The magnification is given by this formula. And similarly for a compound microscope, m is equal to m naught into me, where m naught and me denote the linear magnifying of the object in the eye lens. Okay, so here we end our lecture. So this is the end of the lecture. Thank you for watching.